You know, when a spacecraft phones home from millions of miles away, it's not just sending back data. The journey itself actually changes that signal, twisting it, warping it. But here's the cool part. For scientists, that garbled message isn't a problem at all. It's more like a treasure map, embedding all this secret information about the invisible universe it just flew through. So how on earth do they read it? Well, that's exactly what we're going to dig in.
So this brings us to the big question, right? How do you even begin to measure something you literally can't see, like a magnetic field or a cloud of plasma that's millions of miles away? I mean, you can't just send a probe to every single spot in the solar system. So instead, you have to become a kind of data detective and learn to read the clues left behind in the signals we get right here on Earth.
And the master key to unlocking this whole mystery? It actually has a name: Faraday rotation. Okay, so imagine a radio wave is like a wave you make on a long rope by wiggling it up and down. That up and down direction, that's its polarization. Now, imagine that wave passes through a magnetized plasma, which is really just a super hot gas of charged particles. Well, that direction gets twisted, kind of like someone turning your wrist while you're wiggling the rope. And the amount of that twist, it tells scientists exactly what that signal passed through. So the bottom line is, this twist is the clue we are hunting for.
Okay, so every investigation has to start at the source. In our case, that's a spacecraft like Stereo A or the Mars Reconnaissance Orbiter. It sends out this perfectly clean, stable, really powerful radio signal. Think of it like a pristine message, perfectly written and sealed in a bottle before it gets tossed into the cosmic ocean.
But just look at what arrives. These graphs show the signal's frequency. In the chart on the top left, you can see that clean, sharp peak of the signal as it was sent. Perfect. But now look at the one next to it. That's what we actually receive here. The signal is no longer a sharp peak, it's broadened out, it's messy, it's full of noise. This right here is our crime scene. Somewhere between that spacecraft and our radio telescopes, something happened, and our job is to figure out.
Now, to crack a case this complex, you can't just wing it. You need the right tools. Scientists can't just stare at that messy signal and see the answer. They need a systematic process, a data detective's toolkit, if you will, to carefully go through the evidence and pull out those hidden patterns.
So the initial investigation is really all about cleaning up the raw evidence, just like a real detective would secure a scene. First, they have to decode the raw stream of ones and zeros into a signal they can actually work with. Then, they strip out any constant background noise, what they call the DC signal, so they can focus only on the important changes. After that, they balance out the different components of the wave to make sure their measurements are accurate. And only then, after all that prep work, can they do the first calculation of that all-important twist, the plane of polarization. Okay, but here's the thing. Not all forensic tools are created equal, right? So the scientists tested a bunch of different methods to calculate that polarization twist. And as you can see in these charts, most of the methods, those are the blue and pink lines, they give these really noisy, scattered results. But one specific filtering technique, which they call Butter-Stokes, produced that clean, stable, red line at the bottom. This proves it's the most reliable way to measure the twist in their test data. So this becomes their chosen method.
All right, so we've got our go-to forensic method. What's the next step in any good investigation? You got to rule out the obvious suspects. We need to be absolutely positive that the twists we're seeing are from plasma out in space and not just some weird quirk of the machinery itself.
And suspect number one, it's actually the spacecraft's own rotation. To keep from overheating, the Stereo A spacecraft was put into this slow, controlled spin of 5 degrees per minute. You can see that effect really clearly in the bottom graph. That smooth, wavy red line shows the predictable pattern of the spin. But because it's so regular, it's not a problem. Scientists can model it perfectly and just digitally subtract it from their data. Easy peasy. And that helps them isolate the real cosmic signal. And this is a perfect way to think about the difference between what we're looking for and what we're not. The spacecraft spin, that's a man-made effect. It's regular, it's predictable, it's easy to get rid of. But the effects from the solar plasma, oh, that's unpredictable, it's chaotic, it's always changing. That is the real, valuable scientific data we're after. So after all this cleaning and subtracting, we are left with a very strong signal. We're talking a signal-to-noise ratio greater than 30 decibels. To put that in perspective for you, that means the actual signal is over 1,000 times stronger than the background noise. It's incredibly clear. But even in the super clean signal, tiny little fluctuations are still there, and this is the good stuff. We've eliminated the noise from the machine, and we're getting closer to hearing the true, subtle whispers from the cosmos. Okay, our tools are calibrated. The usual suspects have been ruled out. All the groundwork is done. Now it is time to apply these detective techniques to a real cosmic event and crack the case of the Martian ionosphere.
So picture this. From our vantage point here on Earth, the Mars Reconnaissance Orbiter, or MRO, is about to pass directly behind Mars. This is called an occultation, and it creates a perfect natural experiment. For just a brief moment, MRO's signal is going to have to slice right through the upper layers of the Martian atmosphere.
And just watch what happens to the data. For the first 25 minutes or so, everything is stable, everything is quiet. But as that signal path gets closer and closer to Mars, the evidence just goes wild. You can see the noise level jumping, the signal power is fluctuating like crazy, and the polarization is changing right before the signal gets totally blocked by the planet. This, right here, is the smoking gun.
The research team double-checked and confirmed no spacecraft operations were happening at this time, so they could deliver their final verdict, and I'll quote it right from their paper. We can conclude that the change in the plane of polarization and the fluctuating frequencies is originating from the Martian ionosphere. Case closed. The invisible Martian atmosphere was the culprit. And this is a huge deal, because understanding this charged layer helps us figure out how Mars lost its once thicker atmosphere and its water out into space.
But you know how it is in science, right? You solve one case, and it just cracks open a bunch of new ones. Every new answer seems to reveal deeper, more fascinating questions. The investigation is never really over. It just moves on to the next mystery. And this investigation absolutely left behind some tantalizing new leads. For instance, why do different components of the signal sometimes rotate in the same direction, which theoretically shouldn't happen? And what's causing this mysterious wave with a period of just a few seconds that they kept seeing over and over? And what's the real source of a 90-degree uncertainty that still pops up sometimes? These are the next cases for our data detectives to crack. And I think that just leaves us with a really cool final thought. Sometimes the most important information isn't in the clean, simple message that's being sent. The biggest discoveries, they're often hidden in the noise, in the distortion, by learning how to meticulously decode the static in between.